Okay, good day. This is AP Calculus. I am Mr. McCully, and today we are doing the presentation for Section 2.2 Differentiation Rules. And after the last one, I hope this one's going to be a little bit shorter. And so let's just get right to it. Okay, so the learning goals. Today we're going to find the derivative of a function using some basic differentiation rules. Then we're going to find the derivative of sine and cosine. You can use the limit definition to get it. It's kind of difficult. We're going to skip over it and just memorize the rules. And then we're going to use the derivative to talk about what a rate of change is. So getting right into it, basic differentiation rules. The constant rule, anytime you take the derivative of a constant, you get 0. And once again, just to review, when you see this where it says d over dx, and that implies take the derivative of what's ever inside the brackets or parentheses or whatever. And so the derivative of any constant with respect to x is always going to be 0. So for instance, if you get just as a, let's say y equaling to 3, and I say we're going to take the derivative of that thing with respect to x, that thing is just going to be y prime equaling to 0. So that's our first derivative of any constant. Now, simple power rule says that when you take the derivative with respect to x of the variable x to some power, you are going to take whatever that power is, bring it down in front, and then you're going to reduce that power by 1. So just as a real quick example, d over dx of y equaling to x to the fourth, and purposefully, excuse me, purposely using a different notation just so that we see all of the types of notation that you might see on the AP Calc test. This thing is going to be dy over dx. Again, these two are essentially synonymous. And then I bring the 4 down, so it'll be 4, and then it will be x to the 4 minus 1 is just 3. And then the constant multiple rule, I'll show you that on the next page. And then the sum and difference rule basically says if you add or subtract two different terms and you take the derivative of the whole thing, it's just the sum or the difference of the derivative of the first function plus or minus the derivative of the second function. And we're going to see that quite a bit. Next, the derivatives of the trig functions, the two basic ones. All of the other trig functions, tangent, cotangent, secant, and cosecant, can be derived very easily just by using these. So as long as you know these two, you can, if you get into a pinch, you can do the rest of them. Okay. In fact, when we talk about the quotient rule in the next section, I'm actually going to use these two as my means for deriving tangent x and to get the derivative rule for tangent x. And then finally, the rates of change, average rate of change versus the instantaneous rates of change. I've used this example before when we talked about the difference between calculus and pre-calculus. When I say average rate of change, I'm talking about taking a whole sum and dividing it by some other measure. And for example, average speed, the time it takes to go from Coshocton to Columbus. Let's say it's 100 miles and it takes 2 hours to get there. Well, we can find the average rate of change of that. All right, we can say 200 or 100 miles divided by 2 hours gives me 50 miles an hour. But if I want to know exactly how fast I'm going 10 minutes into that journey, then I have to see exactly how fast I'm going 10 minutes into the journey by looking at the speedometer. And it makes sense that if you're going from Coshocton to Columbus, there's lots of stop signs, there's stoplights, there's different changes in speed limit. So your speed is going to change based upon where you are during that journey. And the speedometer will give you the instantaneous rate of change at any point during that journey. Okay, so that's my analogy there. So let's get right into some examples here. And for this first one, I'm going to kind of go through all of these rules that I have all up here, and I'm going to break it down and do it very explicitly. And then the rest of them, you're going to see me starting to take shortcuts, kind of slamming some of these together. And so if you have questions over these, please feel free to ask, and I'll break it down again for you. Okay. So looking at this thing, the first derivative, well, I have the sum, or the, excuse me, the difference here of two different functions, and then this x to the first power is being multiplied by a constant. So if I want to take the derivative of this function right here, or this expression right here, 3x minus 1. The sum and difference rule says that I can take the derivative of the first and add or subtract it to the derivative of the second. So this thing is going to be equal to the derivative with respect to x of 3x minus the derivative with respect to x of just 1. Now, the constant multiple rule says that if I take the constant times some function, so 3 times the function x, I can bring that constant out in front. So I can rewrite this as 3 times d over dx of just x minus d over dx, the derivative with respect to x of just 1. Now, the derivative with respect to x of x, remember this is to the first power, so it's going to become 1 times x to the 1 minus 1. And then the derivative of a constant is always 0. Now x to the 1 minus 1 is x to the 0. Anything to the 0 power is 1 times 1 is 1 times 3 is 3. And so my first derivative, f prime of x, that's what that is 3. And now that makes sense. Now think about it in this context right here. I need to change my properties of this line. It's too thick. Okay, there we go. Think of it in this context right here. The line 3x minus 1. 1, 2, 3 on the x-axis. That's supposed to be a 3. It's not a very good one. 1, 2, 3, negative 3. 1, 2, 3, positive 3 on the y-axis. Starts at negative 1, goes up 1, 2, 1, 2, 3 over 1. And so I have a line that looks like this. Okay? This thing says that the slope of every tangent line, because that's what the first derivative does. This thing, or the first derivative at its basic level, finds slopes, and that's a terrible spelling of slope. Come on, Macaulay, get it together. S-L-O-P-E, there we go. Finds slopes of tangent lines. All right, now this tangent, or this line, does not change in slope. So at any point, the slope of this tangent line is going to be 3. The slope of this tangent line is going to be 3 because the slope never changes. It's always 3. So that's literally what this first derivative is telling us. It's telling us that the slope of any tangent line, or the slope of the function, is always 3, which makes sense because we have a linear equation. Okay, now let's start slapping some of these rules together. All right, so I see that I have a constant, I have a simple power rule, I have a difference, a simple power rule, a sum, a constant multiple, and a simple power rule, all in that one. So I'm going to go right to it and say f prime of x is equal to 2 times, I'm going to use the simple power rule saying 3x to the 3 minus 1, and then it's going to be minus 2x to the 2 minus 1 plus 3 times 1x to the 1 minus 1. And that thing's going to simplify to 6x squared minus 2x to the first, which I wouldn't write. And again, anything x to the 0 power is 1, so this is going to be 3. This is my first derivative. All right, moving on. I think I skipped my trig function, No, I didn't. For some odd reason, I thought I skipped those. Here they want me to take the first derivative. They want me to find g prime of t. So I have a constant times a function that I know. Pi, even though it is an irrational number, it is still a constant. So this thing is going to be pi times the derivative of cosine t. And from this, we have the cosine of t equaling to negative x. And therefore, excuse me, negative x, but in this case we're using the variable t, make sure you use the variables that they give you. So this is negative sine t, and so my final answer for g prime of t is going to be negative pi sine t, and that is my solution. All right, here now in this one we have a little bit of difference, and they want us to rewrite, differentiate, and simplify. Why? Because we need to rewrite it, right? Rewrite this function so that it fits one of these basic rules of differentiation. And so for me to do this one, I need you to recall that x to the negative n is equal to 1 over to the x to the n, and the reverse is also true. So I am going to rewrite this thing as y equaling to 2 over 3 x now to the negative 2. And now I can use the simple power rule. And when I do that, do the differentiation, it becomes y prime equaling to 2/3 times negative 2x, and then it's negative 2 minus 1, and that is a big error management. I see a lot of kids who, when they first start doing this, they make the mistake and they say that, but when I reduce this by 1, I get negative 1. Okay, these are negative numbers. Negatives get smaller by 1, they go down further. And so my final answer for this is going to be y prime is equal to negative 4 over 3 x. Oops, I already know it's the negative third power. Let's do it all in one step. I got negative 4 over 3, and then to make my exponent of my x a positive value, because negative 2 minus 1 will be negative 3. If I push it to the bottom, it becomes positive 3. And that is my final answer there. All right. Now, here's one. We have a rational function, which is a polynomial divided by a polynomial. And you will notice that there are no rules where I have a variable expression in the denominator. So I'm going to have to rewrite this some way. A mistake that happens often is students will try and derive the top, and then they will try and derive the bottom, and that is a mistake. Don't be that guy. Before I can do this, I am going to use the property, the fact, that a over c plus b over c is equal to a plus b all over c. When we add fractions, we can only add fractions if the denominators are the same, and when you do add them, you add just the numerators, but you leave the denominator the same. So I'm going to use this fact, and I'm using it that way to rewrite it one time. So this is still h. H has not changed. This is going to be 2x squared over x minus 3x over x minus 1 over x. All right. So here I'm going to simplify each fraction. And so I still have h. I have not done the derivative yet. No prime. So this is going to be 2x. This is going to be minus 3. And this is going to be minus x to the negative 1. Now I can use the basic differentiation rules. And since I am going to do the derivative, it now becomes h prime. The derivative of just 2x, it's x to the first. 1 times 2 is 2. 1 minus 1 is 0, so that becomes just 2. The derivative of a constant is always 0. And then it's going to be negative 1 times negative, making that a positive 1. And then it'll be x to the negative 2. And so my final answer, h prime of x, is just going to be 2. And then it'll be plus 1 over x squared. Now this is okay. But remember, if you want to make this into one fraction, you'd have to multiply the 2 by the funky one, x squared over x squared. h prime of x is also equal to 2x squared plus 1 all over x squared, and that's a single fraction. Those two are equivalent. All right, last one. I think there's an error here, so I want to change this just a little. I want to rewrite this as y equaling to x to the third minus x. And this says find the values of x where y has a horizontal tangent line. All right, now I know something about this function right here, okay? Just off the top of my head, I know that, let's make that a little smaller, that is a first degree polynomial. I know that it's going to kind of come down here like this, and it's going to go up, and then it's going to go down like that. Now that's not perfect, I know, but in fact, I think since I think I want to have a double root. So just because this is the internet, let's make it a little bit better. I'm going to have something that goes like this. It's going to come up, and then it's going to touch and go back down. That's what it's going to look like. Now, where does this thing have a horizontal tangent line? Well, if I make a horizontal line, and I don't want that second one, where's the horizontal tangent line? Well, there's one, right? There's a horizontal tangent line. And where's another place where I'll have a horizontal tangent line? Well, there's another place where I'll have a horizontal tangent line. So finding the horizontal tangent line, at least the x values, that tells me the x value where the function is either a relative maximum or a relative minimum. And so this is a process that we're going to use a lot. Finding where there are maximums or minimums, or finding the maximum value. And just in general, anytime they say find a max or minimum, you're thinking derivative, set the derivative equal to 0. And that's going to be something that we're going to do quite often. So taking the derivative of this particular expression right here, I'm going to get, and just me saying, again, using the notation over and over, or different notation from time to time, because I want to make sure that you're seeing all of the different notation. Yes, I could put y prime if I wanted to, but I'm going to say I'm taking the derivative of y with respect to x. So dy over dx, that's our notation. We've done the derivative using the simple power rule. This is going to be 3x squared, and then this will be minus the derivative of just x is going to be x to the first. Now, again, horizontal lines have slope m equal to 0. So since this thing is the function, this is the one that finds the slope of all tangent lines. So if I set it equal to a value and set it equal to x, that will find all of the x values that has a tangent line equal to that value. In this particular case, we're looking to find where the slope is equal to 0. So I'm just going to take this value and go 3x squared minus 1 equaling to 0. I bring the 1 over, that'll give me 3x squared equaling to 1. Then I go x squared equaling to 1/3. And then I can say x is equal to plus or minus the square root of 1/3. Yeah, that works. And so I am going to have relative extrema. I'm going to have, so the slopes, the values for x, where y has horizontal tangent lines is at x equaling plus or minus the square root of 1/3. That's not a very good one. All right, folks, that is it. That's all I have. I will answer questions. And once again, if you think that I made an arithmetic mistake, that is quite possible. Please leave a comment or email me, and I will try and get her fixed. So you guys have a good day. Thank you and goodbye.